So I would like to present a bit Lp-cohomology, mainly for Lie groups, but not for all Lie groups, for special families of Lie groups. And it's a work with Bertrand Rémy. And so I plan to try to motivate a bit and to explain a bit how Lp-cohomology can be used. So I start with a very general setting, but I will skip. I will soon consider more special case. So to start with, G will be a locally compact second countable topological group. So with these properties, then yeah, I should consider also P, which is a number larger than 1 and smaller strictly than infinity. And then one can form Lp of G, which is the set of function, measurable function from G to R, such that the integration of U of G over P dg is finite. And this dg here will denotes the a left invariant R measure. And we consider also pi from G to so the right regular representation that is pi of U applied to pi of G applied to U, which is U of yeah, okay. I need some more. Let's write it like that. So pi of G applied to U at the point X is U of XG. So one has to note that pi is a isometric representation if only if G is unimodular. Okay, because here I have taken the left invariant R measure on the right regular representation. Okay. So so it differs from Ursula talk, but for Ursula in Ursula Emmenstadt talk, the group was discrete, so there is no is unimodular. Okay. So now I define the Lp-cohomology. So Lp-cohomology of G. So it will be so HK. So it will be the continuous cohomology. So it's as usual. It's the kernel of some dk divided by the image. and where so CK is so it's the continuous function from G power K plus 1 to LP of G. And I take the invariant space, which is by definition, so the set of function from Gk plus 1 to Lp of G, which are continuous and equivariant. So f of G times x naught Gxk is pi of G, f of x naught Xk. And D is the usual differential operator, dk, of f. So at x naught Xk plus 1 is the sum from I to 0 to k plus 1 of 1 minus I f of x naught xi, that I forget, xk plus 1. Okay? So this is the usual simplicial differential. So I gave the definition for people who are not familiar with this, but I will not use it. Okay. Okay, so what is it good for? So one result that can motivate his study is this theorem by Elek, and then generalized to the topological group, unimodular topological group by Sauer and Schroeder, and to every topological group by Bertrand and I, which tells you that, so let G1 and G2 be as before, so locally compact second countable. And so when I equip them with metrics, then I can speak on quasi-isometry. Then every quasi-isometry F from G1 to G2 induces canonically the graded topological isomorphism from the cohomology from the continuous cohomology of the second one to the continuous cohomology of the first one.
Is this full tutorial?
In which sense? So,
like the composition?
Yeah, for composition, yes. In principle, it's functional. Okay. So one can use Lp-cohomology to study quasi-isometries. And I want to illustrate this by a not very well-known theorem by Consu, which is about Heinze group. Yes.
So how should we think about this there? I mean, if the group, if you replace this with, let's say there's a nice locally finite simplicial complex that's associated with these groups, right? Then you can think of this as ordinary homology, right?
Yes, yes. Lp-cohomology of simplicial complex.
But if the group that is not NP or something like that, then
Yeah.
Then how should one think about this?
So if the group acts properly on let's say simplicial complex, which is contractible, then the Lp-cohomology of the simplicial complex, co-compactly, of course, the Lp-cohomology of the simplicial complex will be the same as this. For example, for compact group, this is 0. So general fact that continuous cohomology with value to every representation is 0 for compact groups.
But in general, so you could look at something like a Ricci complex, right?
Yes.
In terms of that, for discrete, but if it's not.
If it is not discrete, for example, if the group is semi-simple, then it's the same as the simplicial cohomology of the symmetric space, and also the same as the Durham Lp-cohomology of the symmetric space. So here, what is nice is you don't have to do any contractible assumption on the groups. But if you want to speak of Lp-cohomology of simplicial complex or Durham Lp-cohomology of manifolds, then to get invariant by quasi-isometry, you need the space to be contractible. But all of them are the same. So under a reasonable assumption, all of these cohomology are the same. So Consu consider the group of the form let's call them RH, which is R semi-direct product with Rn, where the semi-direct product is given by so alpha is to the automorphism group of Rn is like so alpha of T. It will be some diagonal matrices matrix. With lambda I, all of them are positive. Then what Consu says is that any so far any two such groups are quasi-isometric if only they are isomorphic. And so H is a means negative curvature, so it's a Lie group of negative curvature, so it's called the Heinze group. And so the classification up to quasi-isometry of Heinze group, now it's a very, very active subject. So several people in this audience are working on, or have worked on this subject. But I think one of the precursors was Hammerstadt, who proved similar results, similar type of results. In our PhD. Physics. So she made one of the first to consider this. So there is consul. And so one of the precursors also was Xiongxi. And there are a lot of people in this audience who work on this subject. So one can assume that so you have lambda 1 smaller or equal to lambda 2, smaller or equal to lambda n. You can always do that up to isomorphism. And then you define WK, which is the lambda 1 plus lambda 2 plus, etc., lambda k. So the sum of the k first eigenvalues. And what Consul proves is that for k at least 2, and of course k, I think smaller than n, so the cohomology with value to Lp of h, so there is a lot of h. So this is it is 0 for p larger than wk wn divided by wk minus 1, and it is non-zero. Yeah, so I do it again. So it is 0 for p larger than this, and it is non-zero for p between this number some interval between this number minus epsilon okay, so and because this is invariant by quasi-isometry, then you get that these numbers are quasi-isometric invariant. And so if two groups are quasi-isometric, then these numbers are the same, and then you will obtain that the eigenvalues are the same up to a multiple, a common multiple. And so now it's easy to see that the groups are isomorphic.
In this proof, you're really, because of your remark earlier about the right regular, the Lp-cohomology is in a non.
Yeah, exactly. For this group, yeah. It's really a point, yes. This non-unimodular.
The group is not unimodular,
Yeah.
so the representation he's looking at an LP.
Yeah, it's not an isometric representation. And everything I will do is to go to non-unimodular groups.
Can you translate this to the boundary of infinity? Or,
not, yeah, so in some sense one can, what that sponsor is doing, but his idea is to represent this cohomology spaces on the boundary, but it's yeah.
But I mean, you can also directly work.
Yeah. So that's why I have, yeah, sure. So I think it's there may be several proof of this result using quasi-conformal geometry. Usually, yeah. So usually the way people are studied this kind of problem is using the boundary at infinity and quasi-conformal geometry. And but for example, there is this question by Cornulier. So he asked whether to study quasi-isometric classification, or I mean, so examples of this for groups, for Lie groups of non-positive curvature. And for Lie group of non-positive curvature, apart those which are comes from semi-simple groups, very few is known. So far. And so you, for example, for them, you can expect to use Lp-cohomology, and it works yeah, a little bit. So now I would like to record another question by Gromov. So it's an old question by Gromov. So it's again in his book, old book. So now let G be a semi-simple Lie group of rank, real rank R with finite center, okay? And Gromov asked several questions about Lp-cohomology of this group. So first question, so is the cohomology of G with value to Lp of G is 0 for every k strictly smaller than the rank and for every p. Second question is what happens in degree equals to the rank. So is H R, so R is the rank, so the cohomology at degree equals to the rank, non-zero for some p. And there is a third question. In fact, for the first question, he really wrote conjectures, not really a question. So is the cohomology at the rank Hausdorff? Which means that when you divide the kernel by the image is closed in the kernel. And so this kind of problem has been studied. And so there are several answers. When the rank is 1, so everything is true. So it's already more or less in book of Gromov. So I can be deduced from Pensu also. So of course the first question is nothing, because the cohomology in degree 0 is always vanishing. So and so we know in rank 1 that this this invariance has some geometric meaning. It is linked with the conformal dimension of the boundary. So what is known also is that the continuous cohomology of G in degree 1 always vanish when the rank is at least 2. So again, it is done in Pensu's paper. And this has been reproved a bit differently and generalized by Cornelier and Tessera. And yeah, there are other way of doing this. For example, to use some general result of Bader, Furman, Monod, Gelander about vanishing of H1 of a semi-simple Lie group of higher rank on every LP space, not only for this special representation. So there is a very recent result by Lopez Neumann, who was a student with Bertrand Rémy on I. So this vanishes here it's for every P. This vanishes for every P when the rank is at least 3 with some, so there are some cases it does not know how to treat so far, with some exemption. For example, I think it does not treat the exceptional groups. And there is a family also that it does not treat. So this is due to Lopez Neumann. And finally, when P is equal to 2, 1 and 2 are true when P is equal to 2. And so there are some results in this direction by Borel, but so general should follow by Bader and so on. So I think I haven't forget anyone. So if I do, tell me. Okay. So I will state a theorem with Bertrand. So theorem with Bertrand. We consider connected Lie group of the form R is equal to A semi-direct product N, where A is isomorphic to RL, and such that two assumptions are required. So first assumption, kind of contracting assumption, is that there exists some psi in A, which is the Lie algebra of A, such that when this psi acts on the Lie algebra of N, so add psi restricted to N, so N is the Lie algebra of N, as probably this is are all its eigenvalues of strictly positive real part. Okay, so it contracts N. So if, for example, if I consider the subgroup generated by psi on N, then I get a Heinze group. And there is a non-triviality part that for every X in in A, for every X in A, when I consider the action of X on the Lie algebra of N, then this admits at least one eigenvalues with non-zero real part. So in particular, so there is no commutation between elements, an element in A and N. So I don't want to, I want some irreducibility in some sense. So such assumptions are satisfies for non-positively curved Lie groups, for example, irreducible without Euclidean factor. No, it does not follow. Why? No, because here there is this psi, so there is one element which contracts everything, and the second one is for every element. So then, in each of the following case, so we don't know how to do it in full generality. One has, so for large P, and first, so the cohomology in degree K of R we value to LP of R is 0 for K strictly larger than the rank. And in degree equals to the rank. So the reduced cohomology is non-zero. So this part can be deduced, in fact, from works of Ponsu. And the interesting part is non-vanishing part. So it says you that you can expect to use Lp-cohomology in degree equal to the rank to study quasi-isometries. Oh, okay. So what are the cases? So the cases are first when R is N is isomorphic to Rn, which means that N is abelian. So in the second case, we prove this when R is equal to 2. So for this kind of group of rank 2. And finally, in the last case, it's for groups of the type it's when AN appears in the Iwasawa part, Iwasawa decomposition. Of a semi-simple Lie group with finite center. Okay, so that's the theorem. And so in the last case, the group R is quasi-isometric to the semi-simple Lie group because what remains is the K part of the Iwasawa decomposition, which is compact. So the cohomology of AN is the same as the cohomology of the semi-simple Lie groups. So you get that the second question of Gromov is okay. So I would like to say some words about the proof for the remaining time. So what is the idea? So the idea is really using in the group on some decomposition. So the idea of the proof, so the idea of the non-vanishing part, let's say, so it's to decompose. So we decompose. So first we decompose A as the part generated by this contracting vector plus some complementary part that you can, for example, take the 1/0 trace and you let B be de Lie algebra of B. And now, what can be said of R? So R, which is a n, so can be written as a group generated by this cross B, some indirect product with n, and I write it like that. And this is equal to B semi-direct product with H, where H is this part, and H is Heisenberg of negative curvature. And so you can expect to say something on the cohomology of R using what is known on the cohomology of H. And the cohomology of H has been studied by Pensu. So the second part is something it's a bit, so it works like that. So yeah. So it's better to take the Poincaré duality. So the cohomology of, so we are interested in the cohomology in degree R of R with value to Lp of R. So by Poincaré duality, this is the same as the cohomology degree D minus R. So D will be the dimension of our group. Yeah, I should take the reduced cohomology. So this is the reduced cohomology. So the reduced cohomology of R with value to the conjugate of Lp, which is Lq, and everything dual. So here, D is the dimension of R. 1 over P plus 1 over Q is 1. And but this is known to be Hausdorff. This part is known to be Hausdorff. Yeah. But it is in fact equal to the non-reduced cohomology. And this happens when Q is close to 1. So here, so one has to make some, so D minus R. So it's also the dimension of H minus 1. And so P is large, which will correspond to Q close to 1. So instead of working with in degree R, I will work in degree the dimension of H minus 1, where it's the LP cohomology of H is not so complicated. And with Q close to 1 instead of P large. Okay, so after, so there is some result by Pensu, and also there is Fubini type arguments. So Pensu analyze the cohomology of H for Q close to 1. And what does it, what he has proved is that so H of so in dimension d minus r, the cohomology of H is non-zero on Hausdorff. For Q close to 1. And is on the cohomology, and it is concentrated in this degree. Anything is 0 for K different from d minus r and Q close to 1. So the cohomology of H for Q close to 1 is known. Okay. So you can expect to say something using the about the cohomology of R using the cohomology of H on a spectral sequence. But the term which will appear in the spectral sequence is not the cohomology of H, it's the cohomology of H with value to not LQ of H, but LQ of R. So you need something. That's where Fubini appears. The cohomology degree, let's say d minus r, or in every degree, in fact, yeah, let's say in degree d minus r of H with value to LQ of R. So this is isomorphic to, so R, I decompose it as a product of A with N, and I use Fubini in some sense. So it's the same as the cohomology of let me see. So H, yes, it's R, which is like that. And yeah, so R, I wrote it like that. So it's the cohomology of B. It is the LP of B with value to the cohomology of H with value to LQ of H. And this works when this cohomology group is Hausdorff, but it is Hausdorff here because it is either 0 or Hausdorff. And now, finally, one can apply a spectral sequence. So the fourth part is a spectral sequence of Hochschild-Serre, which tells you that the cohomology in degree R, continuous cohomology of degree R of R with value to LP of R So because R decompose like that, and so it will be expressed as the cohomology of B with value to the cohomology of H. But the cohomology of H, as we saw, even when I take the coefficient here, it is 0 everywhere unless the degree is D minus R. So it's really concentrated in 1 degree, which is D minus R. So I should compute this as I saw before. So I want to compute this for Q close to 1, but as I said, the part of H, its cohomology is concentrated here in 1 degree. So you will get the H0 of B with value to the cohomology in degree D minus R of H with value to LQ of R. Okay, so that's what the spectral sequence gives you. And then you apply what you have seen. So of course, this is the same as these things. So the invariance. And now you take this isomorphism. Okay. And in some sense, you take the invariant. So if you take the invariant, then so of course B acts on this by conjugacy. So what you get here is that this is so the psi, which belongs to this cohomology of H. Oh yeah, it's not K, it's such that when you integrate it over B, you conjugate by psi and integrate it over B. It's Q dB. This is finite. And yeah, this is the conjugacy. Okay, so so proving it is 0 or not, it can be read on the cohomology of this Heinze group. And now the analysis starts, because now you have to find classes there with this property. And now, so recall that this is the dimension of H minus 1, so it's dual of the H1 in some sense. And so you can read this cohomology on the boundary of H. And so the boundary of H is N. And so this can be expressed as some volume forms. So you use the Durham cohomology So volume form on N with some properties. And okay, so you have to construct. So it's easy for N. It's also it's not very difficult for when R is equal to 2. And so for this case, we used the previous case, and it's more a case-by-case analysis of all the types of semi-simple Lie groups. So we don't have a general result, which we would prove. In fact, we would prove the general statement, namely this result for every n groups, which satisfy this property C on NT, if we would know how to construct some C1 function, so compactly support C1 function on nilpotent groups, was when you so you would like some non-zero C1 function compactly support on nilpotent groups, such that if you have a priori some left invariant vector field on the group, you would like that the integration of this function along every orbit of this left invariant vector field is 0. And it's not so easy. Maybe you have heard about this kind of problem. I've never heard about it, and I've asked. Left invariant. So you take a family of left invariant vector field on a Lie group, and you would like to construct a C1 compactly supported non-zero function, such that its integral along every orbit of this vector field is 0.
It is a particular class of vector fields, or you need just all left invariant vector fields?
So yeah, you can restrict to some of them, but the general problem is for you start with a family of vector field, a finite family of vector field, and you would like to do this. Okay, so thank you.
Thank you very much. Are there other questions?
I had a general question about the introduction to your talk that you gave about the motivation of Lp-cohomology. You present this example of the Heisenberg group where you could use these Lp-cohomology to distinguish them up to quasi-isometry. So I was wondering, is there any case where, so as Mario pointed out, there one could conclude the same thing by studying the boundary and quasi-conformal geometry of it using techniques of Jeremy Tyson. So are there cases where Lp-cohomology gives some information that you could not directly extract by looking at the boundary?
So for Heisenberg group, you would like some kind of quasi-isometric classification which are not known by other methods. So for Heisenberg group, I don't know. But for this Lie group of non-positive curvature, yeah, you can construct some family of groups of non-positive curvature. So it's explicit family R2 semi-direct product R3. Not all of them, but in such a case that every two groups in this family that are quasi-isometric are isomorphic. And the way of doing this is using this invariant. So the rank here is 2, and using the Lp-cohomology in degree 2. So it is not for p close to 1, it is 0. and then it becomes to be non-zero, and the critical value is enough to distinguish the groups of the family. But there is no bond. Yeah, there is no analysis on boundary so far.
Welcome back, everyone. So the next speaker is Kai Rajala. He's going to talk about uniformization of metric surfaces.
Okay, I would like to thank the organizers for the kind invitation. Congratulations. I will talk about some extensions of the quasi-symmetric parameterization theorem of Bonk and Kleiner. First, what is the parameterization problem? You assume that X is a metric. So the parameterization problem in general says that if you have a metric space, the X is homomorphic, I will only talk about S2, then find homomorphism from X onto S2 with good analytic and geometric properties. There are many classes of homomorphisms one could consider, like bi-Lipschitz class, which Stefan mentioned yesterday. If we talk about quasi-symmetric homomorphisms, we give a definition. So homomorphism between metric spaces is weakly quasi-symmetric if this distortion inequality holds, which means that the image of every ball is uniformly round. So another parameterization problem in the quasi-symmetric class becomes how to know if a given metric space is quasi-symmetric equivalent to the standard two-sphere. This is a difficult problem, which is very much open in general, but Marian Bruce solved it for all for two regular spheres. That's the famous Bonk-Kleiner theorem. So again, X is homomorphic to the two-sphere, and all for two regular. That's the assumption. Then there's a quasi-symmetric homomorphism from the space onto S2 if and only the space is linearly locally connected. Yeah, Halford-2 regularity means that the two-dimensional Hausdorff measure of every ball is comparable uniformly to its radius squared. So the Hausdorff-2 measure behaves like a Lebesgue measure in the standard two-sphere. And the LLC I'm not going to define. It's basically the same as what Pekka was talking about yesterday. But it is a connectivity condition which rules out cusps or ridges. So it's a quantitative connectivity condition on the space X. If you know that the space is alpha 2 regular, then there's a very clean classification when you know a very clean characterization when you know whether or not you have a quasi-symmetric parameterization. It's kind of the fundamental theorem of quasi-symmetric parameterizations. One could take many different directions from here. In particular, one can ask whether the same result holds in higher dimensions. So if you have alpha n regular space, moment to Sn, it's a geometric condition like the LLC condition, which guarantees the existence of quasi-symmetric homomorphisms. Such a condition like the LLC is clearly it's easy to see that it's necessary for the existence. But this is not true. It was also already a counterexample was already provided by Steven Semmes in '96 in dimension 3, and Juha and Yang Wei Wu in all dimensions, and then Pekka Pankka and Yang Wei gave a class of a wide class of examples in all dimensions of spaces that are geometrically nice but do not admit any quasi-symmetric parameterizations. So the Bonk-Kleiner theorem really is a complex analytic theorem in the sense that it depends strongly on plane topology. And it also looks like the uniformization theorem about conformal mappings, except that there's a condition on the space, and then there's a strong conclusion, stronger than conformal. You actually get a global geometric conditions properties. Well, the classical uniformization theorem says that if you have any smooth surface without any conditions, then there's always a conformal homomorphism, which only has infinitesimal control of the distortion. So we ask, is there a theorem like this, which is even closer to the uniformization theorem, maybe without any geometric conditions on the space? So does the classical uniformization theorem extend to metric surfaces? In other words, when is the conformal homomorphism from X metric surface onto the two sphere? There's two problems inside the problem. First, what is a metric surface, and then what is a conformal map in this context? Metric surface, it would be nice to be able to uniformize any metric space homomorphic to the sphere, but that's impossible. So here we consider, basically we rule out fractals. So we assume that the two-dimensional house of measure is finite. That's the minimal assumption we make. And then what is conformal? The first observation is that since we definitely want to include known spaces or known planes, we must allow quasi-conformal mappings because known spaces are not conformally equivalent to each other, typically. So we need to apply quasi-conformal maps where the distortion is bounded instead of equal to 1. And another observation is that whatever reasonable definition of quasi-conformality you use, the Bonk-Kleiner theorem solves this problem in the case of alpha to regular LSE spaces. Because whichever definition you use, then by results of Juha Heinonen and Pekka Koskelan, the similar results by Steven Stems and David Stems, the quasi-symmetric mappings and quasi-conformal mappings, the classes are exactly same if you have alpha to regular spaces with LLC condition. So we want to extend this to more general surfaces that still have finite area, but not alpha to regular. Then what is the definition of quasi-conformality? The easiest way to define quasi-conformality would be just take an infinitesimal version of the quasi-symmetry. That's the metric definition. But it turns out that this is not the correct definition in our generality. It doesn't work well, and you cannot construct such mappings. One can take, for instance, two spheres and then stick thin cones to it and study and see that the metric definition fails. So instead we use the so-called analytic definition, not geometric definition, which are equivalent. So for this, you find the upper gradient first. So rho is an upper gradient of a map phi. Yes, this would be defined a couple of times already. If phi of x minus phi of y distance is at more the distance. Let's say distance. Get more the integral of the function rho over any path gamma x y that joins x and y. So this kind of a way of finding maximal stretching of a mapping and also regularity of phi. Now we can define what's conformality. We can say that the definition the Homer phi now from x plus 2 is the quasi-conformal if two conditions hold. First, phi has an upper gradient rho in L2, this kind of solar regularity. And then there's a distortion inequality. And for the gradient, you take any set E on the domain X, integrate the upper gradient squared, you have that this is at most k times the area of the image. It's for all model sets E in the domain. Yes. So yeah, thank you. The reference measure will always be 2-dimensional Hauser measure. Best write it that way. This is a soft way of saying that the maximal distortion squared is at most k times the volume derivative at almost every point. This definition works much better. Now, another question is, if you are given a metric surface, so homomorphic test to and finite two-dimensional Hauser measure, when can you find such homomorphisms? That's uniformization problem. And the result I proved 2017 was a characterization of when such a homomorphism exists. So it's not clear, but it's actually true. So if you have this condition, then the inverse also satisfies the same condition. The converse does not hold, and that is important here. So yeah, if the inverse is quasi-conformal in this sense, then this map does not have to be.
Just because
Yeah, the target has to be Sn. That's important. Yes. Yes. The theorem is that there's a you see Homer phi from x to S2. If and only, well, there's a condition x satisfies something called reciprocal, which I'm not going to define. Instead, let me say that a sufficient condition is the following. Upper bound on the mass area, so H2.
You can start.
Okay, let me 1 minute. Thank you. The area of any ball is at most constant times the radius squared. So if you have this condition, then you have a quasi-conformal mapping. So maybe you can switch to now. No. Yeah, that's a good point. So if you don't assume any conditions, then you get except this upper bound, then you get a quasi-conformal mapping. If you in addition assume LLC, then by the Bonk-Kleiner theorem, you actually have a quasi-symmetric mapping. So the same mapping, which is quasi-conformal, is also quasi-symmetric if you have more conditions on the geometry of the space. There are several aspects of it that have been improved by several people, like for instance Sylvester and Peter Pozzi-Corradini. And in particular, Matthew Romney proved that if there exists a quasi-conformal map, then there's always a pi/2 quasi-conformal map, which is the sharp constant shown by the L infinity norm plane. Lütschak and Wenger also applied the general theory of solution to Plato's problem. In this case, in the two-dimensional case, it gives another approach to the uniformization problem. In particular, it gives another proof for the Bonk-Kleiner theorem by using minimal surfaces, as well as my theorem, which again is another approach. So one could ask if any space, any surface satisfies this condition here, but this is not the case. The simplest example is that if you take a sphere, you take the unit disk inside it and shrink it to a point, then it's easy to see that this, well, the space, the decomposition space that comes then, it's homomorphic to the sphere, but it cannot be quasi-conformally equivalent, again, by any reasonable definition. So then the question comes, is there still a way to relax the quasi-conformality condition and get the uniformization theorem that holds for all surfaces? So how to extend uniformization to all metric surfaces? Here the condition comes from the Lütschak-Wenger theory. So we define weakly quasi-conformal mappings, which are continuous, surjective, and monotone. So not exactly homomorphisms, but close. The primes of every point is connected. G, now the order is reversed. Now the domain is S2. We say that it's weakly quasi-conformal if it satisfies the same analytic conditions as the quasi-conformal mapping. So same regularity and distortion assumption. And now kind of the ultimate theorem on this quasi-conformal uniformization is this answers a question by Stefan and myself, by Dimitrios Balabekos and Matthew Romney. And before Damaris Meyer and Stefan prove it under mild extra assumption that every metric surface admits a weakly quasi-conformal uniformization. So this, as far as I am concerned, this solves the uniformization problem in this setting. Of course, there's fractals and everything one could consider and will consider. Let me try to illustrate this a little bit with an example of multiply connected plane domains and their decomposition spaces. If you start with a domain D on the two-sphere, infinity connected, so that's interesting. You can always, there's an associated decomposition space which shrinks all the complementary components points, for just the disk example I had earlier. And then there are many ways to put metrics on the decomposition space. One easy one is you fix a continuous weight omega on the sphere, which vanishes, which is 0 exactly on the complement of the domain. So I guess the conformal change of metric outside the complement in the domain. And then the distance is the length distance associated to the weight. So you take any, if you're given 2 points, you take any curve that joins them and integrate the weight over the curve. That gives you a metric on the recomposition space. And if weight is bounded, which I assume here, then this shrinks the space, in particular it shrinks the complement of the domain. So this so-called picture shows that you can use the complement of the domain kind of to take shortcuts. That's the idea. Which means that much of the space then gathers around the complement. So this resulting space is again topological sphere by Moore's theorem. It may or may not be conformally or quasi-conformally equivalent to the standard two sphere. Usually it's not, because if there's a lot of complement, then the upper bound I had back there does not work, and you can show that you cannot have any quasi-conformal parameterization. So now the weakly quasi-conformal parameterization theorem is kind of a converse. So if you're given a metric surface, then what it says is that it kind of comes from this kind of a construction. So the weakly quasi-conformal map is that's the projection map, and the upper gradient, that's the weight. That's the idea. It's not quite this simple, but that's the idea. And again, there's many directions one could take from here. For instance, one can ask that, which is much more difficult. If you are given a space that comes from a surface that comes from this kind of a construction, the projection map does not need to be locally invertible in general, but one can ask, could it be locally invertible outside a countable set of points? That's a special case of the classical Kirby conjecture. I'll not talk more about that. Instead, let me discuss some recent joint work with Damaris-Meyer. So what we are doing here is we are trying to understand, again, maps with distortion bounds like quasi-conformal maps, but without assuming that they are homeomorphisms. So complex analytic functions and things like that. There's a slightly amusing issue about the definition. We need to define lower gradients for this to make sense. Because if you try to use the analytic definition I presented for non-homomorphisms, there are several problems that arise. Because for non-homomorphic mappings, you would like to kind of use differentiability and stuff. You use differentiability and stuff in the Euclidean case much more heavily. So what we came up with instead was a concept of lower gradient. But to motivate this, first we can easily notice that the upper gradient inequality I had earlier, the definition is equivalent to this inequality simply by the definition of path length and triangle inequality. That if you have a map, then rho is an upper gradient, rho u is an upper gradient if the length of the image of every path, rectifiable path, is at most the integral of the upper gradient along the path. Now, this can easily be reversed. I mean, you can try to reverse it. You can define a lower gradient by just reversing the inequality. Now, it's a different thing if this makes sense or not. It does not make sense for functions, for real valid functions, because functions usually the level sets are curves, which means that if you demand this inequality, you get only 0 functions as your lower gradients. But but if you're working with mappings where the domain and the targets have the same dimension, then this makes more sense. What this means is that while the upper gradient represents the maximal stretching of the mapping, the lower gradient represents the minimal stretching. So then you can, you can talk about distortion using these two things. I don't know what it means. And what we do here is we want to generalize some basic properties of mappings, topological properties to our setting. So we define mappings of finite distortion. These are mappings from subdomains of the metric surface onto the plane, or into the plane rather. We say that it has finite distortion if we have the same regularity assumption, upper gradient 2, and then we also assume a distortion bound. So now it looks like upper gradient is smaller than some function, finite almost everywhere, times the lower gradient. So this is a different way of saying in the Euclidean case that the maximal stretching is bounded by k times the minimal stretching. This turns out to be much more useful in our setting than the earlier analytic definition. Of course, they are equivalent in the plane. Everything is equivalent in the plane, in the Euclidean plane or sphere. So if X is the standard two sphere, then this definition is exactly the definition of one definition of complex analytic functions. So this class of mappings of finite distortion generalizes complex analytic functions. It relaxes the distortion. You can have, whatever you want as your distortion function. I assume sense preserving. So the sense preserving, well, it could be analytic, but sense preserving, we rule out to begin with all kinds of foldings. So no foldings allowed. That's what it means. So in this setting, in the Euclidean setting, Ivanitsas-Verak proved that if you have a non-constant mapping like this, and if the distortion is integrable locally enough, then F is not only continuous, but it's open and discrete, which means that open sets get mapped to open sets, and the premise of every point is a discrete set inside the domain. For complex analytic functions, this is proved in probably almost every complex analysis course. Analytic functions are discrete and open. And this is kind of the most general result of this type. So the most general distortion bound you can put on the mapping so that it is still discrete and open. So this results in complex analysis, but also in non-linear elasticity theory, where I was working at the time. This result is essentially sharp. Namely, if you take the so-called Ball's map, which is the simplest way of shrinking a segment to a point, then this map almost has this integrability. The distortion almost has this integrability, but not quite. So what we do with Tamaris is that we are able to prove this result replacing the S2 on the domain with any metric surface. If you have any metric surface, same assumptions, then the same conclusion still holds true. And if the distortion is bounded, in other words, if F is a quasi-regular mapping or mapping of bounded distortion, then one can prove this theorem directly, almost directly, using the weakly quasi-conformal parameterization because if you are given such a map, you can decompose with the weakly quasi-conformal parameterization. Then you have a Euclidean map. You can show that that's still quasi-regular, and you can use the Ibanez-Verag theorem or whatever Euclidean result of that nature. But if you make any integrability assumption of the distortion, then this approach does not work anymore, because if you decompose with the mapping, then the no integrability condition of the distortion is reserved unless you have a bi-ellipsis mapping. Another comment is that usually non-homomorphic parameterizations are easier to find than homomorphic ones. In this case, you can show quite easily again that if you have a map with bounded distortion, so a map like this with the distortion is bounded, then you actually have a homomorphic map as well. So you have a quasi-conformal parameterization. This is essentially Stoilov factorization. Finally, you could ask if the existence of a map with a non-bounded but integrable distortion, you can make the same conclusion, and you cannot. So you can play around with the Ball's example, change the metric, and find a surface X which admits mapping and satisfying our assumptions, but which cannot be quasi-conformally uniformized. So, I don't want to say anything about the proofs, except that let me just mention that proofs are largely based on the core inequality on metric surfaces. So in our case, if we look at real valid functions, the classical core inequality of Federer, there are lots of generalization, but I guess in our case, Federer is enough. It says that if we have a Lipschitz function, then the length of Lipschitz function any Borel set inside the domain, then the length of level set inside E integrated is at most 4 times pi times the integral of the local Lipschitz constant integrated over the set E. We recently, with Perelman, Smiley, and Toni Ikonen, generalized this to Sobolev functions with upper gradients in L2 and LP more generally. We prove that if you have a function, again, which is monotone and has upper gradient in L2, actually we have LP version 2, the same conclusion holds, but now instead of the Lipschitz constant, we have the upper gradient integrated, which we need to find these parameterizations and study their properties. Unfortunately, well, I had a monotone on the blackboard which meant a different thing. So the terminology is not great, but for functions, what I mean by monotone, I mean that a function which satisfies maximum and minimum principle. So if we have a function that satisfies a maximum and minimum principle, then without any geometric conditions, we can prove that in the core inequality, the Lipschitz constant can be replaced with the upper gradient. This is not true in general without the monotonicity assumption. And the last thing is how can one use these inequalities? If you're just given a surface which is homomorphic to S2 and finite area, then it's a non-trivial problem to find any curves inside this surface. so that you can apply the upper gradients and stuff. But this can be done using the covariant inequalities. One can, for instance, take some distance function and then show using the covariant inequality and plane topology that inside the level sets of this distance function, you can find plenty of rectifiable curves. And they are even parameterized, so you can start doing estimates. And the idea is the same. If you these kinds of functions typically rise if you minimize some energy involved in including the upper gradient. So finding some kinds of harmonic functions. These functions can be found just by abstract nonsense. And then again, using the covariant inequality and some other plane topology, we can, I think, say surprisingly a lot about them. So this, I think, the main kind of the most important analytic tool that we can use to prove properties for mappings of functions without any geometric conditions. That's all I had to say. I wanted to say thank you.
Are there any questions?
So this may be a little naive, but what's the relationship between the mapping classes that you were considering here at the end and quasi-regular maps?
So what was the first one?
So you define these weakly quasi-conformal maps that are allowed to, you know, they're not homeomorphisms. What's the relationship to quasi-regular maps? Is there one?
So they are quite different in the sense that for quasi-regular maps, the premise of every point is totally disconnected. But then, like compensating functions, it doesn't have to be connected at all. And for weakly quasi-conformal maps, they are always connected, but they don't have to be. The premise doesn't have to be totally disconnected. The component doesn't have to be trivial. So they're kind of orthogonal in that sense.
Thank you.
How do the lower gradients come into play, or where do they come into play? Can you say a word about that?
I guess the main thing is that if you want to prove that at almost every point where you have a path traveling through the point, so the image is a constant path, the whatever gradient has to be 0, and it's easy to prove the lower gradient is 0 just by definition. So then if you make a distortion bound, then the upper gradient is also 0.
Okay, thank you.
Yeah, it's very I mean, I don't know how to do these things just using the Jacobian or volume derivatives and stuff. So this kind of motivates the definition.
Thanks.
Thanks. So how important is it to have these both sided estimates in this definition for all curves instead of, for example, for almost every curve? Does that play a role? Do you in fact consider mappings that satisfy this the upper gradient inequality and the lower gradient inequality for almost every curve?
It's the same thing. I just wanted to overlook all the technicalities.
Right. Okay. Yeah.
So in fact, we use the minimal upper gradient, the maximal low gradient, and work with those.
Okay.
Welcome back, everyone. We are ready for the grand finale with Professor Mario Bonk. He's going to talk about green functions in metric measure spaces.
Yeah, thanks, Enrico. Yeah, you just heard what happens if you're punished with my last name here. And well, I have to make a disclaimer. You know, if we have another power outage, there's no way, you know, that I can continue my talk with the black points. So, yeah, okay. So I want to talk about green function metric spaces, or rather metric measure spaces. And as you will see, this has a more kind of analytic theme. And well, I will try to give you some kind of an impressionistic view of the topic, because there's no way, you know, that I can just discuss all the details. I hope it will not degenerate into some kind of Jackson Pollock type canvas, but let's see how it goes. Yeah, let me start with some credits and reference here. So this is a joint work with Luca Capogna and Zhao Danzhu. We have a preprint, but it's not quite up to date. So what I will talk about is actually some new developments here that didn't make it into the preprint. But well, I hope we will have a new version over the summer. And it's actually quite appropriate that I'm talking about this during this conference here dedicated to Bruce's work, because this all started in some sense during a visit from NYU already 6 years ago. So Bruce and I, we were interested in some kind of rigidity questions for quasi-conformal maps on some exotic spaces like the Laxo space. And somehow, you know, while we were discussing this, we ran into some kind of analytic problems that had actually to do with some Green's function on some exotic spaces like this. And at the time, we already had a outline, you know, for the main theorem that I will discuss today, at least for some exponent range, namely for exponents p greater equal to. And then later, somehow, I learned that actually Luca and Zhao Dan, they are thinking about similar things. And, you know, then we decided to join forces. And of course, we asked Bruce whether you wouldn't be interested in joining, but you were too busy at the time with other projects, I suppose. Maybe you also thought that the whole thing is a bit thin. It is. Maybe I should say it was, because there are some new ingredients here that might be interesting. And this is why I will be talking about this here today. So let me start at the very beginning, right? So let me remind you, what is a Green's function? And, you know, this is probably what you remember from, I don't know, a basic complex analysis course, right? Usually you first encounter Green's functions on regions in the complex plane, right? These Green's functions have a pole. And the main property is that, well, outside the pole, the function is harmonic, right? It means that the Laplacian of the function vanishes. And then at the pole, there's some kind of singular behavior. So you start to plus infinity in the plane. Typically, you have a kind of logarithmic behavior, as we will see in a moment. And then the important thing is that you require that in some sense, the boundary values of the function vanish. And this is a bit technical if the boundary is thin. So I don't want to say more about this, right? So you have to somehow make sense of this condition. And I will not discuss this further today because I want to brush these kind of technicalities under the carpet. Right, so as I just said, I mean, harmonicity, of course, just means that the Laplacian vanishes. But in a moment, we want to make sense of these things in a more general and metric space setting. And there, of course, you know, it's impossible to talk about second order derivative. So in order to make sense of this, we have to somehow translate this into the distributional version. And you do this by writing this in the distributional form like this, right, where this phi here is a test function. So in this sense, let's say C infinity smooth with compact support in U, right? So this condition here is just equivalent with this. And in the metric space setting, I mean, we will be able to make sense of this condition, but not out of this condition. So this is how you should think about harmonic functions. Let me also say that very often by some kind of convergence argument, you can extend the class of phis that you can feed in here, right? So later, actually, we will feed in arbitrary Sobolev functions, well, with some vanishing behavior near the boundary. So let me already say it at this point here. Right, I mean, and then some general remarks here, right? I mean, maybe you remember Green's functions don't exist for all regions, right? The complement of the region has to be somewhat thick enough in the appropriate sense. It has to have positive capacity. But if you have these conditions, then there's a uniqueness theorem for a Green function, namely up to a multiplicative constant, it's uniquely determined. Another way to think about Green's function is as fundamental solutions of the Dirichlet problem, right? Well, they satisfy this kind of distributional equation where at the pole you have a Dirac mass singularity. But I will not pursue this point of view here today, but I just wanted to mention it because this is certainly something that you've all seen in some form or other. Well, today, actually, I will not be interested in these type of Green's functions that you all know. I will be interested in what I like to call unbounded Green's functions. So again, we prescribe some pole here in the complex plane. And now we want to look at a function that is defined on the all complex plane minus this location of the pole. And now we again require that if we approach the pole, then the values of the function approach plus infinity. But if the point runs to infinity, right? I mean, if it escapes from all compact sets, or if the distance to the pole approaches infinity, then you want to require that the function actually goes to minus infinity. Okay. And well, I mean, if you think about this for a little bit, I mean, then you can show this theorem here, namely, unbounded Green functions of this type are exactly essentially logarithms up to scaling and addition of some kind of a constant. Right? So the proof is actually kind of a nice exercise here of the level of, I would say, moderately difficult qual-type problem. So in the complex plane, you can use complex analytic methods. I mean, let me just throw in some keywords here. I mean, you can look at the complex, not complex, the harmonic conjugate of the function. You look at periods, and then you can cook up some auxiliary holomorphic functions, and then you get this result out of this. So this is not super hard to prove, and it's more on the level of an exercise. Okay, so as I said, eventually I want to move to a metric measure space setting. So let's do this one step at a time. So let's go to Rn. And of course, the concept of harmonicity makes perfect sense in Rn, but actually I don't want harmonic functions that are harmonic in the sense that their Laplacian vanishes. I want to consider the conformally invariant case. And what this means in Rn is that instead of looking at L2 Dirichlet energy of my gradients, I look at n energy, namely, I raise the gradient of the underlying function to some power. And this is somehow the quantity that I want to minimize, let's say, with suitable boundary conditions. And if you look at the associated Euler-Lagrange equation, then you get this equation that just specializes to, the Laplacian if n is equal to 2, right? But if n is not equal to 2, you get some kind of nonlinear equation, right? This is called the n Laplace equation, and these are the kind of harmonic functions that I want to consider. So I want to consider n-harmonic functions. And, again, in a moment, we want to move to a metric measure theoretic setting. So it's good to rewrite this second order type equation in a distributional form, and then it looks like this. So let me take this as a definition of an n-harmonic function in Rn. So if I have a function on some region in Rn, then I call it n-harmonic. Well, if this kind of equation here holds for all test functions, and I have to make some suitable regularity assumption on my function. So some local Sobolev regularity with right exponent here is the appropriate thing. So W1n just means I have distributional derivatives, distributional partial derivatives of first order, and they are locally in Ln. I mean, if you think about this 1 second, I mean, then you see that this then here makes sense. And actually, as I mentioned before here, you can extend the class of these functions that you can feed into the equation here. You can extend it from the smooth function with compact support to, let's say, Sobolev functions that vanish near the boundary of U, right? So this will be important in a moment. So let me just say it here. Oh, okay, so this is somehow the notion of harmonicity that we want to work with. And once you have this notion of harmonicity, then you can make sense of unbounded Green's functions again. And let me just tell you that the reason why you maybe want to consider these n-harmonic functions is the relation to the quasi-conformal world, right? So in the plane, it's an easy effect that if you have a harmonic function and you precompose it with a holomorphic function, and you get something that is harmonic. And the n-dimensional analog of this is that if you take an n-harmonic function and precompose with one quasi-conformal map, then you again get something n-harmonic. If you precompose with the quasi-conformal map, then you get something that is not n-harmonic in general, but it satisfies a very similar type of equation, the so-called aharmonic equation, but let me not go into this. So this effect here actually is very useful. So for example, this kind of philosophy that pullbacks of n-harmonic functions under one quasi-conformal maps are again n-harmonic has been used by Gehring to prove his famous theorem that one quasi-conformal maps on Rn are actually Möbius transformations. It's actually very appropriate that I mentioned this here Because if I remembered right, Gehring in his paper, he used results by Di Giorgio that had just been proved about the regularity of elliptic equations. And I think and immediately after Gehring noticed that he can actually use it together with this kind of philosophy here to prove his famous theorem. He actually did use these kind of Green's functions that I will define in a moment, but he just somehow used them to improve the regularity of these one quasi-conformal maps. So in his case, they just had some Sobolev regularity, and he used elliptic theory to promote this to suitable smoothness, and then he could feed it into some classical work of geometers to prove his famous theorem. Yeah, okay, so let me now give the rigorous definition here. So yeah, in my talk here, for the rest of my talk, I will look at these so-called unbounded Green's functions, and I soon will drop this word unbounded here. So I don't have to worry about continuity property because it follows from the regularity theory of my equations that whenever I have this harmonicity here, will I get continuity automatically? So I can always assume that my functions are continuous. And again, I have some kind of prescribed pole, and I want to assume, yeah, this would be Rn here. I want to assume that the function is enharmonic on Rn outside the pole. Near the pole, again, I want to have some blow up. The function should go to plus infinity. And well, if I approach infinity, then the function is supposed to go to minus infinity. And one can again prove that on Rn, you get exactly the same type of functions as before, namely essentially just a logarithm up to a kind of multiplicative and additive rescaling. Yeah, I don't actually know who proved this first. I mean, there's some reference here, but probably the result is even older than that, right? I would not be surprised that it goes back all the way to the 50s or something like this. Yeah, let me make a point here. So as you see, the main theorem that I want to prove is actually the uniqueness of these type of Green functions in a metric measure space setting. But the issue that I will have to struggle with is twofold, right? First of all, I have to get my hands on this multiplicative constant, right? This will require normalization. And then I also have to worry about this additive constant, right? So if I want to prove a uniqueness theorem, I have to worry about these two things here. Okay, so now let's state our main result. So as I said, this is joint work with Luca Capogna and Zhao Danzhu. And our setting is this. So we have some unbounded Arthur's P-regular P-Loebner space. And I don't even want to define these terms because essentially they were defined before. So you all know what Arthur's P-regularity is. P-Loebner just means that the space satisfies a P-Poincare inequality. And I want to somehow say, you know, I don't want to repeat Arthur's P-regular P-Poincare inequality. I just want to combine this into this phrase P-Loebner, right? So for me, P-Loebner is a P-Arthur's regular space that satisfies a P-Poincare inequality. And yeah, the exponent range here is for P between 1 and infinity. And well, our statement simply is, well, then if you prescribe any pole, then these unbounded Green functions exist, and they are unique with proper normalization. So in other words, if you have two of them, then they are always related by an equation like this, well, with appropriate constants. Okay. The original argument that we had was only for P greater equal 2, and this was also related to the discussion with Bruce that I mentioned that we had 6 years ago. Essentially, we followed an argument by Baller, Kolopine, and Tyson, who proved the similar things for Carnot group. For Carnot groups, in Carnot groups, you have a little bit of extra structure because you can use homogeneity. So this was one of the issues that we had to struggle with. I mean, there is no kind of homogeneity. So they made a little bit of use of this. So, you know, part of our argument was somehow to replace this with something else. But, well, the proof only worked for P greater equal 2. But, you know, I gave a similar talk at the Jun Kigami birthday conference in Japan in the spring. And, you know, well, on my flight, they had a lot of time to think about our theorem. And one of the developments is that we now can get rid of this restriction and actually prove the uniqueness for this full range. And there's one new ingredient that is kind of interesting, namely the so-called Clarkson inequalities. I will tell you more precisely what they are in a moment. I've never used them before myself, so this is somehow an exciting kind of new ingredient for me, and I want to somehow share this excitement with you, you know, what you can do with these Clarkson inequalities. Okay, so yeah, I think I have to say a little bit now about, you know, how do we even define Green's functions in this setting? And again, you know, I will be very brief with this. The good thing is, you know, if you're the last speaker, I mean, then you can rely essentially on all the things that we discussed in previous talks, and I will make shameless use of this. So this was all mentioned before, namely, if you have a PI space that is doubling, which is certainly true for our Loebner spaces, then you get a so-called differentiable structure in the sense of Cheeger. And I don't really want to go into the details of this because this is a little bit of a technical subject. Then we just say that from this theory, if you get something that is called a measurable cotangent bundle, and well, essentially for each Lipschitz function, or more generally for each Sobolev function, you get some kind of a measurable differential, almost everywhere defined, that can be considered as a section in this kind of a bundle. The values here are in some Rn's, well, where this n is uniformly bounded, right? So you can think of this differential sitting in some, let's say, well, originally in some Banach space, but in a moment we will actually put it in a Hilbert space. Namely, we have a somehow natural pointwise defined norm on these fibers of the measurable cotangent bundle, and this was also mentioned in one of the previous talks. Namely, you could take, for example, the pointwise defined Lipschitz function, a Lipschitz constant, right? And this gives you a norm here. But what will be important for us in a moment is that actually this norm is comparable with uniform constants to an inner product norm, right? So one way to think about this is, well, you take your unit a ball on the fiber and just replace the unit ball with a John ellipse. This gives you somehow a canonical inner product. And since the fiber dimensions of this measurable cotangent bundle is uniformly bounded, you somehow get uniform constants here, right? So if you want, you can replace this norm here by an inner product norm, right? And you have an inner product that you can use here. Once you have this, then you know, you can completely repeat this kind of previous discussion in this general setting. Namely, now you can define harmonic functions just by this kind of distributional equation here, right? So you have a function, you assume some suitable Sobolev regularity, which makes total sense here in the setting. You have an inner product, and then you can again require this distributional equation for suitable test function. And here now take Sobolev functions that somehow vanish near the boundary of U in a suitable sense, right? So you have a natural notion of harmonicity, and well, then again, you can just define unbounded Green's functions exactly in the same way. You have a given pole. You require that the function is harmonic in the complement of the pole, and you have the right type of blow-up if you go near the pole, or if your point leaves you know, all compact sets eventually. Okay, so this all makes sense in this setting. So before I continue, are there any questions at this point? Okay, so somehow this is the main thing to remember here. There's this kind of equation that we will be using, and actually we will be using it not too much. I think only once or twice in the whole discussion. Okay, so now let me give you the main ideas of the proof. I mean, I will devote actually the rest of my talk to this. There are two parts, right? I mean, existence of these Green functions and uniqueness. And somehow the existence part is in some sense the boring part because there are essentially no new ideas, right? So essentially what you do is, let me draw a picture. You do some kind of exhaustion. So you have your given pole, X naught, you know, and what you do is now you put some kind of large annulus, right? And you solve the Dirichlet problem with suitable boundary values, and then you somehow shrink this inner component of the annulus to the pole, and you know, you let this expand to infinity. And if you well play with the right boundary conditions and you use suitable compactness properties, of these harmonic functions, I mean, then you can show that the sublimit exists and gives you this kind of unbounded green function. There's a bit of a subtle point. Namely, if you want to implement this scheme, you somehow have to choose the right boundary values at the boundary of these annuli. This is a bit tricky. And in order to somehow choose the right values, it's actually good to look at the uniqueness proof first and somehow see, you know, how the function should behave. And once you somehow know how the function should behave, I mean, then you can actually feed this information in to get an existence proof. But I will not say more about the existence proof because this in some sense is completely standard and there are really no new ideas. So I want to focus on uniqueness. This is the more interesting part. And for the rest of my talk, let me just set this up here. So we will have an exponent between 1 and infinity. We will have an R-force P regular P Löwner space, right? I mean, the P here is the same P as here. That's important. So we're in this conformally invariant case. And well, we have two green functions with this pole. And well, I mean, by essentially elliptic regularity theory, we can assume that these functions are continuous, right? So we have this continuous green function with a pole. And now we somehow want to show that, well, up to normalization, you know, these functions are the same. And here's the scheme of the proof, right? First of all, I mean, we have to somehow worry about this kind of multiplicative normalization, right? And I will tell you that you can find the right multiplicative normalization by using P capacity. This is pretty much the same as what Bamler-Kleiner and Tyson did. I mean, they somehow used the same type of idea. Once you have the right normalization, then you can use these kind of capacity estimates actually to show that the difference of these two green functions is uniformly bounded from above. Yeah? So this will be the second part of the argument. And again, I mean, this pretty much follows these ideas of Bamler-Kleiner and Tyson. I should say, you know, C here for the rest of my talk will be a constant that will change from line to line and will not, well, in this case, for example, depend on the functions, of course, right? All right, so you know it's not so hard to complete these two steps. So then you at least get function value differences is uniformly bounded. But essentially, what you want is that the function value difference is a constant, right? So where does this come from? And for this, you somehow have to control the oscillation of this function value difference, and oscillations are controlled by somehow energy. So you need good P energy bounds. And in the case P greater or equal to, one can show that actually this P energy of the difference is uniformly bounded from above, right? And this then somehow allows you, well, to complete these steps 4 and 5 that I will talk about in a moment. But somehow this approach did not work in this range between 1 and 2. And you might say, well, I mean, is this range really so interesting? And the answer is yes, because for these type of spaces that Bruce and I were interested in, for Laxo spaces and so on, you exactly have this type of exponents, right? So you really want to have a theorem that applies to this situation. And the new ingredient here is that really these kind of Clarkson inequalities come to the rescue to somehow save the argument. I don't know whether in this range between 1 and 2 you still get this. At least I can't prove it, but I can prove something weaker that will be good enough to implement these steps 4 and 5 of the argument. So what are these steps 4 and 5? Well, somehow these P energy estimates that I will prove are good enough to somehow show that the oscillation of the function value difference of my two Green's function has to somehow die out if you go towards the pole, if you go towards infinity. Namely, you can show that this difference has a limit as you approach the pole, or a limit as you approach infinity. And once you have this, then you're essentially done, because then you feed it into some kind of careful capacity estimates to first show that the limits have to be the same. And then, well, you apply the maximum principle to somehow argue that the function value difference actually has to be this constant given by the limit. Yeah, I will not say anything about this part 5 here. So this is, again, exactly the same as what Bamler-Kleiner and Tyson did. Right, so this is somehow believable that, well, once you get this far, there's an argument. So yeah, I will focus on these points 1 to 4, well, as time permits. And again, I mean, 4, I will just give you a vague idea what is going on. So yeah, let's get going here, and let's start about thinking about this multiplicative normalization. And the key concept here is the concept of capacity. I should say P capacity, but our exponent is fixed, so let me just say capacity. So the setup is this. So let's say I have an open set. I have some set that is relatively compact in this open set. And then I get what is called a condenser. And I can define the capacity of this condenser essentially as the infimum of the P energy of all Sobolev functions, well, that are bigger than 1 on this smaller set K and less equal 0 on the complement of U, right? I mean, schematically, you should think about the picture like this. I don't know. So, you know, this is your space X. I don't know, you have some, well, this is the function phi, right? So you have some compact set here. You have some larger set U, and essentially the functions that you want to consider are functions like this, right? I mean, they should be greater equal 1 on K, and less equal 0 on the complement of K, and you look at the energy on this ring, right, on U, and you somehow want to minimize this. In nice situations, and I don't want to even say what I mean here by nice, there's some technicalities that I want to brush under the carpet. You can actually compute this capacity from a p-harmonic function with the right boundary values. Roughly speaking, I mean, if you have a function that is p-harmonic and has the boundary values 1 on the boundary of K, the boundary value is 0 on the boundary of U, I mean, then you can just look at its energy and you get the capacity out of that. Yeah. Okay, so that's somehow a standard concept here. And we will use it in combination with the following lemma, namely, if you have a green function, unbounded, of course, and, you know, it has this pole at x naught, then actually, if you look at the condenser that you get from 2 levels of the function, let me draw a picture of what I mean by this condenser. So, well, so we have our pole here, right? And you should think of the function going to plus infinity in a continuous way if you approach this pole. So the super level set of this beta that you see there will be something like that will play the role of our compact set, right? So this will be the set where the function is greater equal beta, right? And then, well, if you go to infinity, the function becomes smaller. So you should think of the sub-level set of alpha as something like this, right? And this this condenser here, this notation refers to this condenser that you have in between here. Right, so that's what we want to consider. And the amazing thing is that there's a fixed multiplicative constant so that you can just compute this capacity from the level difference here up to suitable powers. Right? And yeah, I think I don't have time to really go carefully into the proof. Let me just say that the philosophy is this, you know, you want to consider this function, is essentially you want to say that it doesn't depend on the interval. So how do you prove that, you know, if you assign a number to an interval, it doesn't depend on the interval? You just have to show that whatever interval you have, and if you pass to a child of the interval, a sub-interval, then the thing doesn't change, right? Because if you then have 2 intervals, there's a common parent, right? So that's the idea. So you just have to show that you know, passing to sub-intervals, this quantity doesn't change. And let me just, you know, without discussing the details here, tell you what the main ingredients is. But first of all, you use that your function somehow has the right boundary values, right? So it is a potential. So if you somehow rescale these boundary values, well, then you can compute the capacity. This is where this equation comes from. And then you cook up some test functions from the function itself and feed it into the variational equation. Yeah, and if you do a very simple computation, then you see that you know, if you have alpha beta, you have any subinterval alpha prime beta prime, then the quantity that you're interested in doesn't change because the difference is 0. Right? So I mean, that's it. right? So that it's a kind of typical computation. You use a kind of variational argument in a clever way by using test functions that you somehow cook up from the function g. Yeah, so let me not say more. It's not important to understand the details for the rest of my talk. But what this now essentially means is that we can put this constant equal to 1. And you know, what this says is you can think of it like this, right? That the capacity is somehow normalized in such a way, or you can think of the energy in this kind of ring domain normalized like this, right? I mean, this was just this equation here, right? I mean, if you set this equal to 1, I mean, then we get these two equations that I stated here. Okay, so this somehow takes care of this kind of multiplicative normalization. Okay, so we found the right multiplicative normalization, and our goal now is to show that with this multiplicative normalization, two such green functions actually only differ by a constant. Right. The next step somehow is to show that these two functions, the function value difference differs by a constant. And here's another important ingredient. Namely, let's look at the oscillation of our green function on a sphere of radius r, right? Let's look at the max, let's look at the min. And what I'm claiming is that the max minus the min is uniformly bounded. So on a sphere radius r, my function cannot oscillate too much. It can only oscillate by a fixed additive amount. And the argument for this is very simple. So this uses the P-Löwner property. Let me just draw a picture to talk you into believing this. So do we have some chalk here? Right, so I have this sphere of radius r, right? And remember, if I move towards the pole, then my function goes to plus infinity. So if I look at the super level set of this big M of r, I mean, then I should think of it as something like this, right? So it will somehow touch this sphere of radius r. So this is where my function is greater equal M of r. On the other end, you know, if I look at the sub-level set of this little m of r, then I should think of it as something like this, right? So it encloses my sphere. So this will be this set. Okay. So, well, what do I have here? If I now look at the condenser in between, the diameter of this super level set where the function is greater equal big M of r, well, I mean, it has diameter at least r. Both of these sets actually touch the sphere of radius r. So this means the distance can be at most 2r. This means that the relative distance actually is at most 2, right? The relative distance is the distance divided by the smaller diameter. And now it's a standard property of Löwner spaces that if you have two continua that have bounded relative distance, then the capacity that you get from these two continua from the condenser is uniformly bounded from below, right? That's really the crucial property of a Löwner space, right? And this gives you this inequality here. Oops. Here, right? This gives you this inequality here, right? This comes from the Löwner property by this geometric argument that I just outlined. On the other hand, you know, we have normalized stuff that the capacity between these levels, you know, is equal to this function here. So if you rewrite this inequality, it just says that the difference here is uniformly bounded, right? So oscillations on each sphere are uniformly bounded. And if you put this all together, then you can actually show that you get a very precise kind of estimate for your function. Essentially, you can compute function values of your unbounded means function from capacity up to a bounded error term, right? Think of, let's say, this little r here to be the unit sphere. And let's assume that the point x here, the function value at the point x is 0, right? And essentially get a formula for the green function up to an additive constant, right? So if you have two such functions, well, then they have to be the same up to an additive constant, right? So from our capacity estimates and this fact that on spheres you have only a bounded oscillation, you get immediately this conclusion. right? So if you have two such green functions with the right multiplicative normalization, then the difference is uniformly bounded, right? So this completes the first two steps of my proof, okay? So now the next step is to get these energy estimates, right? Remember, this was the third part of my argument. And let's somehow set this up, right? So now let's suppose we have two such green functions, and let's suppose that they are normalized in this sense, and with the right multiplicative normalization, that if you look at the energy sitting between two levels, then the energy is just the level difference, right? So for the rest of this argument, right, alpha and beta are arbitrary here, but think of alpha and beta for now as fixed, but the difference being very, very large, right? So we have a very, very large M here. And what we would essentially like to show is that if this M is very large, then for the energy of the difference, we get something that is kind of small compared to M, right? This will be our goal. So we somehow want to control the oscillation of this, and what it boils down to, as we will see, is to somehow try to show that compared to this M, this expression here is small. So how do we do this? We use a kind of well-known idea, namely, let me maybe draw it as a picture here. Right, I mean, we are in some LP space. This is a uniform Banach space, right? And we have some kind of a minimization problem, namely this minimization for the P energy. And essentially what we have is, okay, so we have some, let's say, ball of radius M or power of M. And what we will see is that we will have some points, X and Y, whose norm is very close to the kind of minimal norm possible. And what I would like to conclude is that the points themselves are close. And as you see, I mean, the enemy is that if you have two such points in a Banach space and you look at the average of these points, so if you look at the point Z given by X plus Y divided by 2, then the points might be far away, but then this point Z here will be kind of close to the origin, right? So in the uniformly convex Banach space, if you have these type of points somehow have minimal norm, but this point Z also has a very large norm, then the points are forced to be close, right? And this is the philosophy that we want to apply. So yeah, let's look at our functions and let's look at this energy. So well, let's look at this condenser, right? And my function G has the right boundary values. It's a P harmonic. So this means it's automatically somehow the energy minimizer. So this M here is somehow minimal energy that I can get from a function with these boundary values alpha and beta, right? But on the other hand, I mean, this function G tilde, right? I mean, it's not far off from my G, right? It almost has the same boundary values, right? And well, from this fact and the normalization and some monotonicity properties of my condenser, I can easily conclude that actually my G tilde also has an energy that is not much larger than this M. So essentially, I'm in this situation that I have 2 points, X and Y, right? And they have almost minimal. I mean, this guy has minimal energy, but this guy has almost minimal energy, right? So now let's look at this point Z in this context. But again, I mean, I can get very good estimates for this Z, right? I mean, the average of G and G tilde. Namely, if I look at the superlevel set of G and the sublevel set of Z, right? I mean, think of G and G tilde almost having the same values, right? So, I mean, this C here is in some sense negligible. So we get these lower bounds here, we get this upper bound. And if you feed this into the definition of capacity, right? I mean, think of the capacity of this condenser as some of the smallest energy that you can get, let's say, with these kind of boundary values, right? And this guy here has to have an energy that is bigger than that, right? And if you put this all together, then you get this inequality. And if you massage this a little bit with the normalization that you have, then you will see that this guy here has an energy that is greater than M minus a constant. Right, so I'm exactly in this situation. You have 2 points that have almost minimal norm. This Z has a fairly large norm. So what we expect then is that the difference should have an energy that is fairly small. Yeah? But what we now need is a quantitative bound for this. And this is where the Clarkson inequalities come in. And here are the Clarkson inequalities. you know, if you see this for the first time, I mean, it looks a bit messy. So let's see here. So I have this range of p's where I want to be between 1 and infinity. And in all these inequalities, of course, the conjugate exponent will be important, and I will denote it by q, right? I mean, well, conjugate exponent means 1 over p plus 1 over q is equal to 1. And my functions here, and this is very important, are Hilbert space valued, right, on some kind of measure space X, and pointwise, you know, my functions are these Cheeger differentials, and this all lives, if I want, in some kind of fixed Hilbert space, right? So I've Hilbert space function values. The Clarkson inequalities are, you know, depend a little bit on the range. So I have one type of inequality for the range between 1 and 2, and another in the range from 2 and infinity. And this Clarkson inequality is somewhat easier to understand. So let me discuss this first, right? So let's put actually p equal to 2. If you put p equal to 2, then you just get actually an equality, namely you just get the Pythagorean identity, right? So this is something that we know. And in some sense, you know, for other p's bigger than 2, this inequality is more or less just a straightforward generalization of the Pythagorean inequality, okay? And actually, this power p here, we like it because the Lp norm, remember, is you take the pth root, but if you raise it to the power p, you get rid of the root. And so essentially, if we take our gradients here, we just recover the p energy, right? So these terms are just these kind of energies that we're interested in. And let's just think of our situation, right? One guy had energy m, the other guy had energy m plus c. Right, so essentially this average here will be m plus an additive constant. On the other end, this energy was greater equal m minus a constant. Right, so in other words, in this inequality, you know, we have an upper bound essentially m plus constant, but this guy already eats up m up to a small constant. Right, so this means there's not much left for this guy. Right, so the conclusion is that this actually has to be bounded from above by a uniform constant even. Okay, so for p greater than or equal to 2, we immediately get that the energy of the difference will be uniformly bounded. For this range, I mean, this is a little bit harder to digest. And let me just, you know, not comment much on it. Let me just use it, right? So this somehow is the harder case. And if you rewrite this in our situation, right, for the kind of set that we are interested in, for this exponent range that we're interested in our conjugate exponent, then you can rewrite it in this form, right? And let's see what it means. Here on this side, we have m. Here we have something that is m plus c, right? So the whole thing will be bounded by this term, m plus c, up to this nasty power. But the nice thing is this power here, q over p, is bigger than 1 because q is the conjugate exponent, and it's actually, well, bigger, greater equal to 2, right? So it's important that this exponent here is bigger than 1. On the other hand, I remarked that if you look at the energy of this guy, then it's bounded below by m minus c, right? So if you throw the term to the other side, then you get this expression. And now comes the important point. Since these constants here are kind of sharp, the main term cancels, right? So the main term will be m to the q over p and m to the q over p here. So you get a cancellation, right? And this means you get a bound where the exponent is lowered by 1. Yeah? This is the important point. So I lose a power here because the main terms cancel. So if I now take the root, then actually, you know, this expression will divide a smaller expression, so I get a power less than 1. Yeah, and that's the important point. So let me write it like this. So if we use the Clarkson inequality, then we get an energy bound that looks like this, with a delta that is actually in the range from 0 to 1. As I remarked before, if p is greater or equal to, then actually we get a constant here, so the delta is even 0. Right? But the main point is, okay, we have an exponent less than 1 here. So if you put this all together, you know, and instead of looking at this condenser that we looked before, but rather look at something that comes from the metric of the space, and, you know, you somehow use, you know, but is not hard to show that you have this kind of logarithmic blow up, at least up to multiplicative constants, then you are led to this conclusion here that my two green functions with the pole and the right multiplicative normalization satisfy this kind of an energy bound, you know, for all r where you have an exponent less than 1. Okay. Now the nice thing is that this can be fed into what I call the oscillation lemma, namely, if you have this sublinear decay of the energy, then you can show that this function value difference has a limit under suitable assumptions that are true here. Yeah, so I formulate this in a slightly more general form. So if you have a function on your space that is bounded continuous and monotone, Kai mentioned this, so I will not even say what this means, but it's true in our situation. Then this energy bound here gives you the existence of these limits. And you know, for some people like Bruce who know Loebner spaces, let me just try to talk you into believing this. So the main idea is actually very, very simple. Then you suppose your h doesn't have a limit. Let's say, you know, there's a curve to infinity along which the function, let's say, tends to 1. There's another curve along which the function tends to 0. So how do we get a contradiction? You know, so h of x, let's say, goes to 1 here is let's say, greater equal 1, and here the h, let's say, is less equal 1. What I do then is, you know, I can look at dyadic annuli. So let's say 2 to the n plus 1, and then I get two continua here, right? And on these continua, my function is a function value difference that is at least 1. But this gives me continua that again have uniformly bounded distance. This means that the capacity here has to be greater equal than a fixed constant, and this means that each function that has this behavior will pick up a fixed amount of energy in this kind of dyadic range, right? So function with this oscillation will pick up a unit of energy in each dyadic range. And this means such a function has an energy that has to have a linear growth behavior in the logarithm, right? But if we assume sublinear, I mean, then this cannot happen. And this is somehow the source of the contradiction. Yeah. Okay, so let me get back to the main proof here. Essentially, we're done now. Yes. No, look. If I have a function that doesn't have these kind of limits and, you know, gives me a situation like this, then the energy will grow somehow linear in the scale. But if I assume a priori that my growth is sublinear, no. Linear growth in the dyadic scales, meaning linear growth in the log, right? The log measures the number of scales in a sense, right? So yeah, here it's very important that the delta is less than 1, right? And this gives me the contradiction. So let's get back to the main theorem here. So essentially we're done now, right? So we found a suitable multiplicative normalization. Our capacity estimates gave us that this function value difference is uniformly bounded. We got these good energy estimates based on Clarkson inequalities, and, you know, then we have the oscillation lemma that gives us these limits. And as I said, you know, now you can essentially apply the argument from Bullock, Holopainen, and Tyson to argue that then the functions have to be the same. Yeah. So this essentially finishes the proof. But how much time do I have? 5 minutes? Because I want to devote the rest of my time, maybe say a little more about Clarkson's inequalities, right? Because this is something, I don't know, I mean, I kind of knew that something like this exists, but I didn't know it well. And let me just very briefly outline actually proof of these Clarkson inequalities in the interesting range. The range p greater equal 2 is somehow, you know, not hard. So let me just somehow stick to the interesting range. And what you do is you first prove an inequality for complex numbers. And the inequality, the version of the Clarkson inequality in this case looks like this, okay? I mean, this is an inequality for complex numbers. You can prove it in an elementary way. And if you open some books on Sobolev spaces, you know, they will spend a couple of pages proving this. But let me make this remark here, namely, if you invoke some machinery, then you can actually give a very, very slick proof. Namely, you can use what is called restore and interpolation. And I just want to advertise this method here, the restore and interpolation. So the way to set this up is this. So you look at little RE spaces essentially on C2, right? So you look at these kind of norms here. Now you consider a linear operator that sends a pair of complex numbers, well, to this kind of things that appear in my inequality, right? And well, I mean, for each a pair of these norms, there's an associated operator norm of my operator, of my linear operator, right? I mean, this is just a standard definition of the operator norm. So this R here depends on the norm in my source space, and the S refers to the norm on my target space. And well, I get from the Pythagorean inequality immediately that from little L2 to little L2, my operator norm is bounded by square root 2, right? I mean, just take the square root of this expression. Another kind of trivial bound is that if I go from L1 to L infinity, right? I mean, I have this inequality, but tells me that this operator norm is less equal 1. And now comes, you know, the restore and interpolation theorem. I will not even state the theorem. I just want to tell you that there is something like this. It allows you somehow to interpolate between these ranges. You have to look at convex combinations of the reciprocal exponents. So take your favorite theta between 0, 1, and look at the reciprocals of this 2 here and the 1 here, right? And well, I mean, if you take the right theta, we take theta equal to 2 over q, well, then you get 1 over p. And if you do this in the image, well, then you get 1 over q. And the restore and interpolation theorem says that if you're in this situation, then you can bound the operator norm from what you get here to from what you get here by, well, this kind of geometric convex combination of these endpoints, right? So this leads to this bound. The amazing thing is this is exactly the inequality that you want to prove if you translate it back to the norms, right? So this is a very slick proof of the inequality that you need. Once you have the inequality, I mean, then you go through a couple of more steps. Once you have the inequality for complex numbers, then you immediately get it for any vectors in an inner product space, right? Because if you take Z and W in any product space and look at the span of these two vectors, then all these vectors that you see are contained in the span, right? But a two-dimensional subspace of Hilbert space is isometric to the complex plane, right? So you immediately get this then for an inner product space. And to get it for these h-valued LP functions that we are interested in, you well, I mean, you invoke another kind of standard inequality. I mean, my time is running up, so let me just gloss over this. You use Minkowski's inequality for integrals. And, you know, with a clever setup, it's just essentially a one-line kind of computation, right? So yeah, let me stop here and let me maybe make one concluding remark here. Okay, now we have this uniqueness theorem for these green functions, right? But now the next question is, I mean, can we do something with it, right? I mean, this goes back to the original motivation that Bruce and I had. The annoying thing is this kind of Cheeger inner product is, of course, not unique. But if the Cheeger tangent spaces are one-dimensional, right? I mean, Sylvester remarked this again yesterday. I mean, we have something unique, and maybe then one can do something with these green functions, right? So I think that would be kind of an interesting topic for further exploration. Yeah, and well, that's all I want to say. So thank you.
Are there questions?
So it's more a side question, but can we express the dual of W1P using the green function you just computed?
I don't know, maybe.
Okay. But do we have the invariance by conformal transformation on the W1P?
Absolutely. Well, right. I mean, this is the whole point. I mean, from the uniqueness, now it follows that if you precompose one of these green functions by a one quasi-conformal map, you know, then again, you get a green function with the pole moved to whatever location. Yeah, that's somewhat the whole point, right?
Okay.
So, well, I guess you alluded to this fact, even though you didn't say it explicitly, with that the inner product structure is not unique on the Cheeger cotangent bundle. But so you could define p-harmonic Green function as p, or these p minimal Green's functions. So you could use this minimal over gradient, and
then the whole argument unfortunately collapses, because it's very, very important somehow that you don't lose any kind of constants here.
Yeah.
Right. So you really have to work with the right norms, because as I said, it's important. Oops, where was my cancellation here? It's somehow important that these main terms in the inequality exactly cancel right here.
Yeah.
Right. And if you have multiply constant here, the whole argument falls apart.
Absolutely. So my question then is, if you have a Finsler manifold, Rn, actually just Rn with a Finsler norm, is it true then that the p-harmonic or the p-minimal Green function would be unique up to this normalization, or is that known even in
for
Rn?
Minimizer.
Minimizer, yeah. Rn with a Finsler.
Oh, with
norm.
a Finsler.
With a Finsler norm.
I don't think so.
Okay.
Yeah.
Thank you.
It's probably inaccessible question in some sense.
Yeah. Well, the general case might in some case be as hard as that.
Yeah,
so if one could solve the Rn case, then there might be a way of.
Well, to be honest, even in the Rn case here, n greater equal 3, I mean, the proof is still fairly, in some sense, this proof here applies in Rn, and I don't know any simpler proof. Right?
Thank you.
Are there more questions?
Thank you. Actually, I have two questions, and the one is very naive, since I'm no expert in metric space analysis. So if I look at open sets in R2, the only case where these results hold is exactly R2, right? Because for the disk, the condition that you put at the boundary, so to speak, is
what result?
The fact that there is an harmonic function with a pole and it goes minus infinity at the boundary.
Yes.
Right. So the naive question is, what in the assumption on the space tells you that essentially you are working in R2 and not on an open set of R2?
Yeah, I see. Well, I mean, essentially, that a point has capacity 0 in this sense. Yeah, that's in some sense very important. Yeah, an open set, if you have an open ball or so, you see the boundary in a capacity sense. But there is no boundary in the capacity sense if you are on the full space R2. That's somehow how this comes in.
And that's encoded on the assumption on the space.
Yeah, I mean, this Löwner property essentially gives you that this kind of point at infinity has 0 p capacity, and implicitly this is very important in the argument.
Okay, then I have a second question, and okay, one could consider in a higher dimension still harmonic functions. I mean, 2 harmonic functions. Yes. And one can ask to classify Green function by the behavior at infinity.
The uniqueness is open in this case. So only in the conformally invariant case, in this case, is the uniqueness known. You can look at other exponent ranges, right? I mean, if you, let's say, call it p tilde, right? Here, my p tilde was equal to p. You can look at other p tildes, but there, the uniqueness is open. And I don't see any way even to approach this question, right? So it's very important that we are in the conformally invariant case here. That somehow, makes the argument possible.
Thank you.
Okay, thank you. So let's say that we can discuss with Mario during lunch, because some of you, I know that they have to catch a flight. So together with Mario, I would like to thank all the speakers and the other organizers like Xiandong Xie, John Mackay, and Zhengjing Huang, or Herskovich and Sylvester Eriksson Pick. But I also would like to thank Sebastiano Nicolosigolo and especially Francesca Tripaldi, that they were the organizers of the last week conference, but because of inertia, they got involved and forced to continue the organization of this conference. Thank you. Thank you to all of you.
One moment. Yeah, before you all go, right? I mean, I'm the last speaker here, so let me say some few words, and then Bruce will also say something, right? I mean, we should thank the organizer for putting this all together. The staff here had a pretty hard time today, so maybe they deserve some extra applause. Let's also thank the organizers again. And let's give a very special applause to the mastermind of it all, Enrico, right?